And so here we are. I guess the YouTube Live is started. So welcome to the whole world. Dear colleagues and friends, ladies and gentlemen, interested laymen, and all the others. It's a pleasure for me to start this series of webinars. This is the ICORR Consortium for Rehabilitation Robotics YouTube channel. And we're proud to start this series of webinar. My name is Claudio, and together with Dr. Kathleen O'Donnell, we will be moderating the today's webinar. So without much further ado, I have a couple of slides to let you know what's going on. So the ICORR webinar series is a series of YouTube Live webinars, which we roughly schedule to happen every couple months. So the next one should be end of March, but expect beginning of April or something like that. And well, what we want to do here is raising awareness about rehabilitation and assistive robotics, showcasing topics and problems and technologies, and most importantly, possibly provide a view on RAR, rehabilitation assistive robotics, to everyone who's interested. And there's a small list of people who might be interested: junior scientists and PhD students, even undergrad. Why not the interested laypersons? That's good. So like I said, this is Claudio Castellini speaking from the Friedrich Alexander Universität of Erlangen-Nuremberg, located in Germany, not far away from Nuremberg, actually. I am a professor in rehabilitation and assistive robotics. Actually, my lab is called Assistive Intelligence Robotics. We deal with mostly interfaces, signal processing, and artificial intelligence driving, rehabilitation and assistive robotics, so prosthesis, exoskeleton, virtual reality, and why not, exo-suits. Dr. Kathleen O'Donnell, would you like to introduce yourself, please?
Gotta unmute myself first.
Yeah.
Hi, everyone. My name is Kathleen O'Donnell. For those who don't know me, I'm the Vice President of Marketing and New Business Development at LifeWord, which until a few weeks ago was called Rewalk Robotics.
Right.
We went through a rebrand recently. And so we commercially develop and manufacture advanced technologies designed to elevate standard of care in physical medicine and rehabilitation. And so most specifically for the purposes of this discussion, we manufacture the Rewalk personal exoskeleton, which enables individuals with spinal cord injury to stand, walk, ascend and descend stairs and curbs during activities of daily life at home and in the community. And then we also developed the Restore exo-suit for in-clinic gait rehabilitation of individuals post-stroke. And this was based on the technologies that Connor and I actually worked together to develop when we worked together at the Wyss Institute and the Harvard Biodesign Lab. So I'm really looking forward to today's discussion, and I can't wait to jump in.
It's going to be so exciting to have the commercial perspective on the technology we'll be discussing about today. So what is the technology we're talking about today? Well, soft exosuits. This is without any pretense of comparison. So soft exosuits is a technology that was, well, actually, I just discovered, invented more than 100 years ago. At least there's a patent for that. And the idea is to overcome exoskeleton, which are, well, powerful and precise mechanisms in which the user, say, slips, but are also bulky. They make a lot of noise and produce heat, and they can be quite dangerous. I mean, imagine your body, your limbs are completely surrounded by the exoskeleton. So if an exoskeleton goes wrong, then there could be dire consequences. And so we're talking here about a new potentiality. So the idea is that we still want to help people move, people with some kind of motor impairment, essentially, stroke patients, spinal cord patients, spinal muscle atrophy, you name it. But this time with the use of button cables, which basically act in parallel with muscles and joints. And actually, I want to thank publicly Dr. Carl Zelik, who commented on a post of LinkedIn by myself, and he let me know that there's a patent dating 1919, soon after the First World War ended, in which basically the principle of an exoskeleton was sketched. Look at that. I mean, I was honestly not aware of that. And it would be interesting as well to have a comment from our speakers about that. And I particularly love the quote by Isaac Asimov: "There is no discovery in science or engineering, however revolutionary, however sparkling with insight, that does not arise out of what we went before." And I think Isaac Newton was the one who said, "I am a dwarf on the shoulders of giants." Well, enough philosophy, I would say. So the idea of soft exosuits is they're less dangerous, they're lighter, they're wearable, more wearable than exoskeleton. But the assistance that they can provide is limited. There's less force and torque that they can add into the human system. So how do we solve these problems? Well, it's my pleasure now to introduce you the three prominent scientists, researchers that accepted to be our guests in this field. To all people who are watching the live streaming of this webinar, please send us comments and questions in the chat. I will be able to see them, well, almost live, because Zoom to iTube Live has a delay of about 20 seconds. So in the turn of 1 minute, your question could be picked up by ourselves and asked, fielded directly to our speakers. Good. Let me quickly introduce to you the first guest we have today. And yeah, there's a bit. So Lorenzo, by the way, is I would say a friend, definitely, besides an excellent colleague. So Lorenzo started out getting a degree in Padua, Italy, and then had a long session at the IIT in Genoa and at MIT. And then his academic path starts as assistant professor at the School of Mechanical and Aerospace Engineering, the MAE, at Nanyang Technological University in Singapore. And that was from 2013 to 2018. And then since April 2019, he got a position as full professor in biorobotics and medical technology at Heidelberg University in Germany, at the Institute of Computer Engineering, the so-called Institut für Technische Informatik, the CITI. And now he leads the ARIES lab. I have visited it, and it's really wonderful, where ARIES stands actually for Assistive Robotics and Interactive Exosuits. I give the stage to Kathleen O'Donnell to introduce the other two speakers now.
All right. So next up, we'll have Robert Riener. Robert studied engineering, mechanical engineering at TU München, Germany, and the University of Maryland in the USA. And he received his Doctorate of Engineering from TU München in 1997. After postdoctoral work from 98 through 99 at the Centro di Bioingegneria, oh gosh, you guys are gonna make me say all this, Politecnico di Milano. He returned to TU München, where he completed his fellowship in the field of biomechatronics in 2003. And then he became an assistant professor at ETH Zurich and the Spinal Cord Injury Center of the University Hospital Belgrade as a double professorship. Since 2010, he has been the full professor of sensory motor systems at ETH Zurich. And since 2016, he's also a full professor at the medical faculty of the University of Zurich. Since 2012, Riener is a member of the Department of Health Sciences and Technology, which he's been chairing as head from 2016 to 2018. He was the guest professor at USC Los Angeles and SSSA Pisa, and he's still the guest professor at SJTU Shanghai. Riener has published more than 500 peer-reviewed journal and conference articles, 36 books and book chapters, and filed 26 patents. He has received 26 personal distinctions and awards, including the Swiss Technology Award in 2006, the IEEE TNSRE Best Paper Award in 2010, and the EU Robotics Technology Transfer Awards in 2011, 2012, and 2021. Riener's research focuses on the investigation of the sensory motor interactions between humans and machines. This includes the development of user-cooperative robotic technologies and virtual reality technologies applied to neurorehabilitation. He is the initiator and organizer of the Cybathlon, which was honored with the European Excellence Award, the Yahoo Sports Technology Award, and 2 Reimagine Education Awards. In 2018, Riener obtained the honorary doctoral degree from University of Basel. And in 2022, he became president of ICORR. And since 2019, he's the AAS Lesnar Leadership Fellow. And since 2023, has been a member of the Swiss Academy of Technical Sciences. And then following him will be Conor Walsh. As I mentioned before, Conor and I worked together back at the Wyss Institute and Harvard Biodesign Lab. He is the Paul A. Mader Professor of Engineering and Applied Sciences at the John A. Paulson Harvard School of Engineering and Applied Sciences, and an associate faculty member at the Wyss Institute for Biologically Inspired Engineering. He's the founder of the Harvard Biodesign Lab, which brings together researchers from the engineering, industrial, apparel, biomechanics, physical therapy, and business communities to develop and translate new disruptive robotic technologies for augmenting and restoring human performance. Example application areas include enhancing the mobility of healthy individuals, restoring mobility of patients with gait deficits, and assisting those with upper extremity weakness to perform activities of daily living, and preventing injuries of workers performing physically strenuous tasks. His multidisciplinary approach spans engineering, biology, and medicine, and has led to multiple high-impact scientific papers. The soft exosuit technology is now commercially available in clinics for gait retraining through a collaboration with Rewalk Robotics, and the lab spin-out Verve has launched a back assist product for workers performing physically strenuous tasks in industry. He is dedicated to training the next generation of biomedical engineering innovators, and lab alumni have gone on to successful careers in academia, entrepreneurship, and high-tech R&D positions within industry.
That's just great. Thank you very much. I actually got you the summary of Lorenzo's CV, so sorry about that, Lorenzo, but we'll have to live with that.
No worries.
I'm told we have 75 people watching live this stream, so you better do a good job, guys. Lorenzo, the stage is yours for the first talk.
So let me try sharing. So if it works now, you should see a nice wolf.
We see the wolf.
Now you see the presentation.
That's exactly what we see. That's perfect.
All right, I'll stay, 5 minutes sharp. These are images, of course, that I generated with DALL-E. They're very good for just from cover page. That's enough. Don't do anything else with that. They are not very, let's say, realistic. However, let me talk today about how to use machine learning in exosuits, and I would like to introduce the concept of context-aware control. If we consider classic approach in controlling softwareable exosuit is classic control. You extract information from motion, from force, and depending if you are on the level of upper limb or lower limb, you can control force-based position or admittance control. Now, how does it work? You detect the force of the interaction, the user, or the motion, and then you close the loop with the actors. You see here, for example, the Harvard Biodesign Lab pioneering this field of robotics and our solutions that we have at Heidelberg University. Over the course of the time, people started also wondering how we can improve the interaction between the user and the exosuit itself, or the wearable technology and exoskeleton. And basically, the concept of subject-specific tailoring assistance was brought to life, specifically from Conor and Steve Collins. So introducing machine learning, extracting data from the person wearing this technology, and then tuning the system in a way to have optimal performance in terms of metabolic cost. Now, since doing better than Steve and Conor is quite hard, let me just offer a different perspective. I'm not following the same approach. A different perspective is not focusing on the user that is wearing the exosuit, but mostly providing the exosuit with what is called context-aware control. It's a way of, let's say, using wearable devices that use machine learning in order to provide the exosuit with capacity to understand environmental change and enhancing user interaction with wearable robotic system itself. How can you do that? Well, for example, you can use the sensors that are in the exosuit to detect the different locomotion modes. You can detect lower ground, ascending stairs, descending stairs. And this is a work that we recently published. Just training the system in recognizing locomotion modes, and then after that, allowing the system to discriminate between level ground. As you can see the red line, level ground. As soon as you step over to discriminate ascending stairs, and the system provides you a better assistance in order to climb the stairs. And then let me stop here a bit. When you pass from level ground again and you go to descending stairs, the system discriminates. We demonstrated that using this context-aware control, you have a high classification accuracy, and you succeed in dramatically reducing the cost of transport while you equip the exosuit with this capacity of discriminating automatically the different locomotion modes. This is something that you can do not only for discriminating stairs, but also, for example, for discriminating seat to stand, stand to seat, and walking itself. There are different, let's say, locomotion modes. You insert pattern recognition model inside the control, and then you run the classic control with this higher layer of machine learning. Here you see the red line is discriminating from the person that is wearing an exosuit. As soon as the person attempts to sit, there's inertial measurement units discriminating this kind of gesture, going down and understanding that the person wants to sit. As soon as she wants to stand again, the system inputs a force and allow the person basically to stand. Recently, there has been also a lot of interest in using artificial vision for awareness, context awareness discrimination. There has been a very nice workshop organized in the last ICORR 2023 by Letizia Gianfrida, Robert Howe, Brock Lachowski, Dai-Kyun Kim, and Michele Xilo-Yannis. So these are examples on how to use vision. Let's say the seminal work probably is from the group of Kyujin Cho on science robotics, but they are doing also very well at the University of Toronto and Toronto Rehab using camera. We use camera as well. We have a camera and using convolutional neural networks to understand what kind of object you want to grasp. And then once the object is classified, the system recalculates the entire weight of the arm plus the object itself and change the level of the assistance. You can do it with upper limb, but you can do it also with lower limb. My group studied how to use a normal camera, non-stereo camera, to understand where you are climbing the stairs, going down the stairs, or walking level ground. And we inserted this kind of camera on the level of the waist. You can see RGB camera that is written here. And then running, let's say, a upper part of the normal control in order to discriminate the different locomotion mode and change automatically what is happening while the person is walking. Here you see the detect ground floor with a higher accuracy, higher than 90%. Descending stairs, see that the camera detects descending stairs. Then ascending stairs with a higher from the models. Also here, to decrease dramatically the cost of transport of the goods. Can you do it without machine learning? Because this is the question. Yes, you can. If you use stereo camera, you are able to train the camera on distance without training the network and understanding instantaneously if the person is ascending stairs with level ground or ascending stairs. See ground floor, classification, no, it's not classification, it's detection. Now ascending stairs and go on. Does these things work in terms of metabolic cost of transport? You still can have a very high accuracy that can be comparable with the one of using machine learning, but you don't have to train any model, and yet you have a capacity of reducing metabolic cost of transport up to almost 20% respect of the exosuit off. Now, what's the idea? Is using this kind of application in real. We are testing extensively our system of Aurora, also in the context of aging. We like also to provide our system with this kind of technology in order to have a context-aware control that works also outdoor and inside the lab. Before closing my presentation, and I hope that I was quite, more or less in time, I would like to advertise, let's say, a twin conference of ICORR, that is BioRob. We have a fantastic editorial team. We received 357 submissions and 27 workshops. We will be from 1 to 4 September 2024. And we invite a lot of eminent speakers in multiple fields, from not only assistive technology, but also surgical robotics, humanoids, and computational biomechanics. I close here my presentation, and I will be glad to discuss with you after the presentation of my other two books. Thanks a lot.
Thank you very much, Lorenzo. Wonderful talk, and yes, almost on time. I take the liberty of adding that the first work you presented was awarded by the Best Paper Award at Rehab Week last year, right?
Yes. Best Student Paper Award. Best student.
Yeah, good. Thank you very much. Second speaker on our roster, Robert, please. The stage is yours.
Thank you. I'm sharing my slides. Now I hope you see something. I want to give a more general talk about the successful use of soft exo-suits, and to summarize with 5 words how I recommend you to make successful soft exo-suits. It is know your goals and users. First of all, one question is, why do we speak about exoskeletons, exo-suits compared to end effectors? Maybe this question can be answered straightforward. The end effectors space systems are easier to use. However, they're usually fixed in space. You have to connect them somewhere in space, which prevents people from walking, from being mobile. That's why we speak about exoskeletons or exo-suits. They are wearable and thus mobile. However, donning and doffing can be complicated in general. Another open question is about why soft, if you could make it also rigid. Rigid exoskeletons are much stronger. However, they're bulky, and most devices do not allow to really sit in a comfortable way. That's a great chance with the soft exo-suits. They are lightweight and they allow better mobility, including sitting. However, the force transfer is challenging, since and this is limiting the function. The force transfer is challenging because everything is soft, and this makes it difficult, first of all, to carry the weight of the system. It has to be carried through the own body, the own bones, and also transferring the loads, the torques, which we need to move or to the device or to support the user. They often result in longitudinal or forces which are tangential to the surface, which are difficult to induce. However, I think we can solve these issues. We can make the systems more functional. And these are my 3 recommendations to provide a sufficient function. First, be sure about your target scenario. Don't develop something which works for everything. For example, we should not over-challenge our tasks. We should not think that people wanna and have to walk and stand all the time. Also, we are sitting now, and also the people with walking impairments often sit in the car, in the living room to watch television, in the lecture room, and so on. So we need to stand up and walk just sometimes, maybe if there are certain obstacles like little stairs, or if people want to stand in eye-to-eye level to talk to other people in a bakery store, for example. So knowing that the people also are sitting quite for a while, we should also take into account this function. For example, be aware that maybe a backpack might not be the best solution for sitting. Second recommendation is select your target group. Do you want to support people with disabilities? For example, stroke patients, they usually have just a hemiplegia or hemiparesis, so you need to support just one side of the body. Do you want to support spinal cord injured people? Be aware that often the injury is not complete. There are residual functions which can be supportive to make the device in a way that we don't need to provide a maximum force or too much force. Or do you want to support just elderly with muscle weakness? Or do you maybe want to support healthy people in sports to make them faster and walk with a less metabolic energy need? So be aware about your target group and design it. And third, exploit the user needs. Talk to the users, talk to the patients, not only patients, or people with disabilities if they are not in a treatment phase anymore, but also talk to the medical experts, to therapists, maybe even to the relatives. What are the real needs of the people who are supposed to use the devices? I'm just at the moment preparing a review paper, and together with the other co-authors, we reviewed around 500 papers. I was really surprised that maybe only about 10% of the papers were mentioning patients, were testing maybe on single patients, and almost nobody mentioned the needs of the patients. And I think that's not only a must to make something which is beneficial for the patients, but also to finally reduce the complexity and develop something which is functional, right? Which is not too challenging and too much. Define the user needs also to make the design process simpler. So these were my 2 cents to this talk. Thank you.
Just great, Robert. Perfectly on time, sharp. Well, we are Germans, are we? So for our next and last speaker, last but obviously not least, Professor Walsh. Conor, please, the stage is yours.
Thanks, Claudio. I'll just share screen, present slides. So thanks for arranging this exciting webinar. So I thought I'd just give a few highlights on the application side, so where we've kind of started with soft exosuits and some things that we've done more recently as well. So my name is Conor Walsh. I'm a Harvard faculty member here, and our group really focuses on developing soft wearable robots. That's a big thrust for our group. So we started working on the soft exosuit early on. It was part of the DARPA program, and the goal was really to try and alleviate fatigue and injury risks for people walking long distances and carrying a heavy load. And I think this video kind of just shows kind of like the idea of the soft exosuit, where rather than using more rigid mechanisms to anchor an interface to the body, try and use textiles and apparel along with flexible cable mechanisms. You can see that there's a lot of compliance here. And so really kind of thinking about going forward for this field, how you really optimize that human suit interface, I think is one of the kind of critical aspects and most challenging aspects. You want it to be as stiff as possible, but you would still want it to be comfortable and flexible. And then the other thing that's kind of like, I think, a critical aspect of soft exosuits is that you can apply assistance when needed, but then the system can be mechanically transparent or get out of the way at other times. And that's because whether you're walking or running or going up or down stairs, as Robert alluded to, you're not doing that all of the time. Sometimes you're sitting, sometimes you're moving around. And so I think the benefit of these approaches is that they really can get out of the way when you don't need the assistance from them. And then we also have tried, with healthy individuals to try and think about how you augment more than just walking. How can you also look at running? And how do you have systems that can get used in the real world outside of a lab environment too? And of course, that just kind of raises the challenge as well. And it's nice to see Lorenzo's kind of group making some nice progress in that area. But after kind of that, we shifted focus. So through a kind of great collaboration with Terry Ellis and Lou Awad at Boston University, and also this was, Kathleen played a lead role in this project during her time at Harvard, really looked at adapting the technology for individuals post-stroke relearning to walk. And so I think kind of the unique aspect here of soft exosuits is that you really can have a system be unilateral. So you don't have to have a system be bilateral like a rigid exoskeleton. You can have a system that's unilateral and really target the kind of part of the body that you want to most focus on. And so we really focus on the ankle joint, because after stroke, that's one of the areas that has the potential biggest benefit for improvement for people. And then in this project as well, you can see that we're really not putting a lot of mass on the limb. So if a person is relearning how to walk, you want them to experience as natural walking as possible. And so I think from a rehabilitation point of view, if we can apply assistance when needed and then allow a person to experience natural walking, I think there's a lot of opportunity there. And then you could also think about having a system get assistance, then be challenged to maintain that while the system is slack or transparent. Or you could even apply resistance with these technologies to challenge people as well. So I think there's a lot of potential and flexibility for these in the rehabilitation domain. Beyond, kind of the more biomechanics studies, studies led by Lou and a former postdoc, Lizette, really looked at the functional benefits. So can people walk faster and can people walk further using these types of technologies? And so we had some nice papers that highlighted the potential of this. I would say the gains are still relatively modest. So, we are seeing some nice improvements in both speed and distance, But I think a question for the field is how much assistance do we really need for people wanting to be wearing these technologies or also buying these technologies? And so what's the cost benefit related to them? I think we've made some exciting progress, but I still think there's a lot more to do in this area. And then I think moving beyond, kind of just the orthotic effect, so the benefit that a person gets when wearing the device, I think the field really still needs to understand what is the rehabilitation potential. So studies led by Lou Awad at Boston University and Arun J. Arman at the Ability Lab in Chicago are studying, with the Restore system that was commercialized by Rewalk, how best to use that in a rehabilitation setting, and can people actually get better when they train with these types of devices. And I think in a clinical setting, I think there's emerging evidence that people can get better using these devices. But I think a big challenge for the field is getting the dose and intensity up even higher. So one thing that we're quite excited about is thinking about how do we take the training with these technologies to the community and outside of a clinical setting, to enable people to do this every day or every second day close to where they live and from the convenience of their home. And so we had one nice study that we published last year, just as a proof of concept with 4 people using an exosuit to practice gait retraining in the community. And then beyond stroke, a recent study that we just got published in collaboration with Terry Ellis is thinking about how do you help other gait deficits. And so this was an exciting finding for our team, where an individual with Parkinson's disease who had a very severe case of freezing of gait, by giving just small assistance through hip flexion with an exosuit, really allows a person to better regulate their walking. And here I think the idea is is this providing assistance, or is this really providing a mechanical cue? So that the person is then able to kind of leverage that and adapt their own walking pattern and style. And I think there's still a lot to learn about how we give small levels of assistance, but still enable big impact from a person, whether that's from a mechanical assistance point of view, or kind of helping a person, kind of optimize their own neuromotor control as well. And then beyond the lower extremity, I think the upper extremity, Lorenzo and Robert's group are doing some really nice work in this area too. Our approach is a little bit different. We're using inflatable wearable robots to help with upper extremity movement. But this is a project here with an individual with ALS, where without assistance at the shoulder, the person can't complete this daily task. But then with assistance is now able to do this. So I think there's a lot of opportunity, but maybe the technologies won't always be the exact same for upper or lower extremity. I think there's still a lot of potential for new designs, both on actuation and interfaces, kind of going forward. And I'll just end by saying, all of this work, I wouldn't be able to mention everyone, is really part of a big team of lab members, past, current, and also kind of collaborators too that I mentioned. And so really kind of it's a big team effort. All these projects are very hard and takes a lot of people to make it happen. So thanks. Looking forward to the discussion.
Just wonderful. Standing ovation. So thank you very much, all 3 of you. Now, just about on time, that's 2:30. So rest of this webinar would be, now having laid a lot of stuff on the plate here, I have a few questions. Kathleen and I prepared a few questions that we'd like to ask you and see what the responses are. I think I might start with a round of one single question to all of the 3 of you. By the way, we have short of 90 people attending this webinar. I want to here once again encourage all people who are watching the live stream, please ask questions. We already have a few of them, which I will collect and make a last round of questions to our speakers, taken directly from the chat. And even comments are highly welcome, of course. So all right. Me not being a mechanical engineer, I'm always fascinated by solutions, smart solutions that involve motors and joints, essentially. So I will just follow up and ask Conor first. So you're planning to build an exosuit for the shoulder, is that correct? How would that? Can you sketch the idea over there? Because I cannot figure out myself how an exosuit would work for the shoulder. A shoulder is a complex joint. It has, someone say, 2.5 degrees of freedom, right?
Yeah, so that's a great question. So I would say one of the challenges with exosuits in general is you're trying to minimize the amount of mass that you put on the person, on the limb. And so I think that creates a challenge with creating multi-degree of freedom systems. So I think in general, if you look at a lot of the work from many groups working on exosuits or soft-wearable robots, they're usually targeting kind of like a single degree of freedom or a minimal amount of actuation. And you're trying to think what is the most you can do with that small amount of assistance. So our approach to assisting the shoulder is really to try and provide anti-gravity support. That's really at the end of the day what we're trying to do. We're not trying to provide full kind of control over the 2 or 3 degrees of freedom of the shoulder. It's can we just offload the weight of gravity of the arm for the user? And I think this would only work for someone who has some residual capacity. So then hopefully they can leverage their residual capacity to try and move their arm either for assistance or for practicing rehab. And our approach is to try and use an inflatable balloon that goes under the arm to try and push the arm up. And then we're trying to do that, but in doing that, try and not constrain the other degrees of freedom of movement for the person. So that's been the approach that we've taken to that.
Robert, please. So all our mics are open, so I would encourage you also to intervene. This is a live discussion, actually.
Yeah, we follow basically the same strategy as Conor does in supporting the movements of the shoulder, especially against the gravity. We additionally have a system which is providing a bit more stability at the shoulder. There's a risk that, for example, the scapula folds out and blocks the movement or hurts the body. And I think that also is, for some patients at least, important. And this idea of supporting with our active components the arm movements against gravity is great. As Conor said, and you are opening flexibility to other movements in the horizontal plane, for example. Plus, in some patient groups, especially stroke patients, you're getting out of some abnormal synergies. Yeah? It has been shown by other studies that you can more independently move the elbow joint when the shoulder is abducted or abducted to the horizontal level, for example.
It's very interesting. Conor, so my second question, but it's you already answered. What would be the future? So what new actuators or principles? You mentioned the balloon that would inflate under the armpit, basically. That's fascinating. Do the others have any? Well, Lorenzo, I mean, I know you also have plans for the shoulder. And on top of that, what is the path to the future? So what new actuators and ideas are on the plate? Well, okay, so disclose too much because we know that the area is very competitive, but still.
No. I mean, the shoulder, I cannot show anything because there was no time, and we are basically trying to patent a new system. So eventually next year, if you would do a webinar, I would glad to try to show if this thing would be successful. For what concerns actuation, I strongly believe that we have right now quite a level of power weight ratio that allow us to go into the spectrum of motion of almost maximal bandwidth of human motion. For what concern instead the utilization of pneumatic or electromechanic, because this is mainly the idea, in my opinion, there should be also a direction of following a hybrid technology. Try to merge the bandwidth, the high bandwidth of the electromagnetic actuators, so electric motors, but also including pneumatic actuation in parallel or in series. I would say that also in parallel can be done in order to provide a sustained action to the system itself. This is something that we are trying to figure it out. But hybrid actuation might be a new solution. Then, of course, I mean, everyone dreams about artificial muscles, nanometric capacity of motion, but this is still science fiction, to be honest. We have to use the technology that we have right now, and I think that we are going towards a good direction.
Now, I'm a fan of Occam's razor, and I want to point it out to all our juniors listening here. The simplest solution which solves your problem, but not simpler than that. This is so Albert Einstein on top of Wilhelm von Ockham. Great. Kathleen, stage is yours. You should grill our guests quite thoroughly now.
I mean, I guess my first question is really, and I think we've all touched on this a little bit, but, you know, just looking at there's a lot of trade-offs when we're talking about exosuits. You know, we want it to be strong. We want it to have high torque. We want it to be fast, but we also want it to be lightweight. We want it to be comfortable. We want it to be, you know, inexpensive. And so there's a lot of trade-offs that we have to do. And I think that, you know, just the discussion that we were having of you know, is it pneumatic? Does it support all the degrees of freedom? Does it just support one degree of freedom? I'd love to hear you guys sort of talk through when you approach a new problem and you're looking at these trade-offs, how do you sort of map that out in terms of these are the things that we absolutely have to figure out a way to do, and these are the things that are more nice to have, and how do you balance those as you approach a new design problem? That's for all three of you. Yeah, go ahead.
I mean, I was the last talking, so I passed the word to someone else.
So maybe I can say something. So as I have shown before, we try to really define the target group and the target scenario very well. And then often you are simplifying the problem. So if you, for example, in many neurological patients, we have incomplete lesions leading to residual functions which are supporting us so that we don't have to produce the strongest actuators. You know, spinal cord injury patients are usually incomplete, but 70% of all spinal cord injury patients have incomplete lesions. Then a stroke is half side and the impaired side is also incomplete. Then many diseases are degenerative, Parkinson, MS, muscle dystrophy. So you can also always find a status where there's still enough residual force. And that helps them to make the system not too strong, not too heavy, not too bulky. And is one, I would say, a rather large population of patients who can benefit from soft exo-suits.
Yeah. And Conor, I think, you know, your recent paper on Parkinson's, I think, is particularly interesting. As you said, you know, it may not even be that we're mechanically assisting as much as we're just sort of doing more of a haptic cue. Is that an example where maybe soft exosuits can really find the right balance in certain populations?
Yeah, I think when you think about training, it's a great question, like training and rehab. You know, a lot of times we do think about like, let's have the device do the restoration. But really what we want is a person to be practicing so they can kind of get better on their own. So I think it's also interesting to think about like, how does a device just help a person know what to be doing and help that person do a little bit more, so that a person is kind of practicing, you know, that themselves. And then maybe the benefit of exosuits is you can take that away and they can still practice as if they have no assistance, and then see kind of what the difference is and be able to kind of start to understand what is good and what is bad. And so I think there's a lot of potential there. And I think it's a great question, Kathleen. And like one thing I was thinking about ahead of the webinar today is, you know, as you know, you worked on our soft exosuit for stroke rehabilitation. We really tried to optimize that to deliver enough assistance at the ankle joint, but keep the kind of part on the waist as lightweight as possible. So that weighs about 3 or 4 kilograms. And so I would say that was somewhat empirical, iterative design that kind of allowed us to get to something that we felt delivered enough assistance that was beneficial, but still wasn't too heavy. But I think one thing that we've been thinking about more recently is if a person is 6'4" and 200 pounds, that may be quite light for them. If a person is 5'2" and 110 pounds, that might be quite heavy for them. So I think it's also interesting when we think about the actuation question is like, should it be one size fits all? Or with these types of devices, should we be tailoring it a little bit more to body weight and size? And then maybe that also opens up other opportunities for devices as well.
That's great.
That's, if I can interject here, that's, oh yeah, so please, Lorenzo.
So, I mean, it depends, just to reply to the question of Catherine, it depends also which is the target of population that you want to exploit this kind of technology. I mean, I am recently trying to focus also on aging and wellness. And there, in my opinion, the approach is slightly different because basically there's the motivational aspect that plays a major role. I like thinking of this kind of technology like, you know, the same history of electric bike that was bought at the beginning by people like my father that used to smoke, you know, an entire package of Marlboro a day and didn't want to pedal. And then you have to imagine instead this kind of technology that is, especially, you know, the electric bike now is used by pro just to climb up higher and then having a better downhill. Same thing for what concerns the exosuit. You should have something, you know, not extremely powerful, but lightweight that provides you in parallel to your biomechanics a decent amount of support. It will motivate people, especially elderly, in, for example, walking the dog for longer time, or if the, let's say, progress of the technology would be very high, you can think about this kind of equipment for mountaineering. So, and that one we go in the spectrum of human augmentation. If you have this kind of approach, it's different from, let's say, the clinical approach, then the requirements are completely different. Yeah, so me, Claudio, who was you were asking something.
I would have, I'd like to, Conor mentioned, rather than assistance, possibly just giving haptic cues. So like now you should attempt the step because that's the right timing. Some of them really lose the idea that the coordination actually, which sort of brought me on this train of thoughts to adaptation and co-adaptation. There's very few machine learning, aka artificial intelligence, in your applications so far. I mean, very little, not that much, I would say. As opposed to, I'm mainly working in prosthetics, and it's the main tool that we have at our disposal. So I understand that users will learn how to optimally use the devices you give them. So there definitely is some adaptation of the user to the machine. How important would it be to have your machine change and adapt its, I don't know, cycle of stimulation or pattern of assistance, or even, of course, in the case of pure rehabilitation, diminishing or augmenting the level of assistance in order to provide a fully fledged assistance needed paradigm? Total silence. Does anyone have an idea here?
For whom was the question? For Conor.
Sort of how important is in the future for you to really use machine learning in order to provide a system which is adaptive also in your case, possibly as time goes by, employing some continual learning paradigm or lifelong learning, they call it nowadays, active learning as well. So the device saying to the subject, hey, I need more data here because you're doing something strange.
I can briefly comment, then I'll add. So these are two, in my opinion, way of interpreting the use of machine learning or adaptability. You want that the system adapt to the person, or you want that the system adapt to the surrounding. I follow more the part related to adapt to the surrounding. Conor was the one basically putting the human in the loop, and he can reply better. But these are, in my opinion, two different strategies that probably are complementary. Something that I can say is that in terms of medical normative, software that change and update, sometimes it's hard to justify for the clinical certification. This is something that happened to me, that I bought a CE certified machine and then I changed literally, the font on the virtual reality. It's lost, the CE certified part. Yeah. So if you have, this kind of change that is adaptive inside the software, this is something that should be regulated, in my opinion, by the medical technology agreement.
We all have our hard times convincing the ethical committees of our institutions that our devices are not dangerous. And of course, the more complicated you make it, the less predictable it becomes. I mean, machine learning is a can of worms. It fails now and then because it's its nature. It should fail.
I fully agree that this is a good question you made, Claudio, that it's interaction between the user and the device. And I think machine learning is a promising tool to take into account this interaction, to include the human into the entire system boundaries, and it's not only the mechanical device or the robotic device. So I think there are chances for using machine learning to optimize these things. Sometimes I think machine learning is not required. I'm not so much a fan of BCIs for daily use. BCI developments are great as a research tool, but to drive a wheelchair or exosuit, exoskeleton, I think there are easier ways or more reliable ways. Even doing EMG to force processing is challenging and maybe not the very best to do. To predict certain gait phases and situations, I think machine learning is a great tool. And what maybe often forgotten is, already in the design process, I think we can optimize things, controllers, but also mechanical components using machine learning.
Yeah, and then the only other thing I would add is that I think with soft exosuits or devices that give lower levels of assistance, let's just say it's 20 to 40% assistance, I think there, where the person has some residual capacity, really trying to understand kind of like what's the device doing, what's the person doing, and what are metrics of success from a learning point of view or a neuromotor control point of view. So I think there's still a lot to do experimentally to try and kind of like understand kind of how you understand that co-adaptation. And then I think we just need better metrics. And maybe I'm not a modeling person, but maybe there's ways that we need to kind of model those types of adaptations the same way people have been really thinking about that for upper extremity rehab robotics. But I think that's I think there's a lot of challenges there. There's a lot of going on. Yeah.
I think I'd like to remind here our audience that so there's nothing really scheduled right now for a series of webinars, but we plan to have at least one on functional assessment. So how do you know that your device is worth anything when you really go into the field? And there will be something about co-adaptation as well. If there's no further comments or questions from you guys.
I had one more that I just wanted to, and I think Robert, you mentioned this a lot, was incorporating users into your design process and how that's sort of not as commonplace as you would hope for it to be. And so I'd like, and I know Conor, obviously you do this as well. I'm assuming Lorenzo, you do as well too. But if you guys could talk about how you incorporate the human in the process, and who else do you include beyond just the end user as you're developing these, and talk a little bit about how that process works.
I think it's most important that you fully understand and know the users, including the user environment, let's say the clinical environment or home environment. And the best way to get to know it is to share your life, to breathe the same air, to stay together, to spend time and space together. In terms of offices, engineering offices in hospitals, medical doctors in technical universities, and so on, to really exchange yourself, to live the life together, to understand these challenges. That's the only way. Just sitting in a chamber and believing you know the needs of a patient, for example, does usually fail.
I have such a hard time convincing my students about that. Stop working in front of your laptop and get out in the field, right?
The only other thing I would say, just that I agree with everything Robert said, but I think we face a challenge as a field in terms of translating these types of technologies beyond kind of a research lab out to the real world. And I think if you work backwards from that, I think what you need to show is like value with an end user in kind of an end user's context, like whether that's a clinic or whether that's the home. So you need to show that. And to show that value, you probably need to run a study. To run a study, I think you need an advanced prototype that you can actually test in that environment and that a person actually wants to wear and can wear on their own. And then in order to do that, I think you need to be kind of working with end users probably for a year at least to really kind of iterate and develop that technology and then make sure it works on more than that one person or kind of like small group of people. So I think it is a real challenge for the field. And so I think sometimes working backwards and saying, where do you eventually want to go? And even thinking about what's the commercial landscape and the commercial reality or the clinical reality in terms of people actually wanting to use these and kind of work backwards from there. And end users are, kind of like the starting point really, but also thinking about where do you want to go longer term.
Yeah, I think Conor, you had a good point in your talk, which is, how much assistance do we really need? And a lot of that comes down to what is the user going to be most impacted by? Is it just better confidence? Is it better speed? What is it that they're going to be most affected by that's going to drive them to want to use this device? And you have to kind of start there and then figure out, okay, how do we actually make that happen?
And if I may also add, we lack of a metric that is universally shared to understand if the device is really effective. I mean, if you take, for example, let's make an example, the walking systems. We cannot just try an extensive trial and keep a person with a metabolic consumption analyzer for the whole day, because he's going to throw the metabolic consumption analyzer to us, including the exo-suit. So we lack of let's say, golden standards that is not too intrusive in let's say, an extended use of the system itself. Yeah,
and I would just throw from the commercial perspective, we also lack something that's understood by sort of insurance companies and reimbursers that are going to pay for this. So we have a lot of work to do.
Good. All points taken, thank you. So I'd use the last, say, 10 minutes in this webinar to pick up some questions from the audience. They've been keeping a steady audience of 75 to 85 people, and I have a few questions here. So rather than making a round, which would make things a little too long, possibly, I'll ask the questions and you just raise your hands if you think you have an answer to give. So Luca Rand asks, could you provide an overview of the opportunities and challenges that you see for European-based medical devices companies That's the competition, I would say. Willing to deploy these systems for home use. For instance, considering the challenges of regulations, reimbursements associated to clinical benefits and competing against suppliers from, for instance, Asia, who are releasing low-cost devices. This is a very interesting question. So devices for home use and opportunities and challenges you see for, well, European, I think Luca is from Europe, but the same question holds for the North American market. This is clear. Robert?
But I don't want to indicate that I know the answer to this challenging question. It's really a problem at the moment in Europe to get the certifications for medical devices if you develop something for the market. And some labs or companies start to develop and to sell then only to the states where it might be easy to get an FDA approval. But maybe it's not a problem that we get now too many devices from competitors in China, because they also have to fulfill the same rules. I just know some competitors or some companies who don't have the CE approval, and they can sell, of course, but you're not allowed to use it then in a clinical environment. But still, it does not solve the problem. It's still difficult and tricky to get the devices approved for the use in home and clinical environments.
That's very interesting. That's very interesting, yeah. There's a few experiments I know didn't really take place, not in this field, but didn't take place in Europe because the rules that European Union sets are really very strict. Yeah. Good. I'll forward you another question from Mr. Srinivas Patwardhan. Sorry about my pronunciation. So this is really, really interesting. Where and how do you draw the line between control exerted by the user on the device and a good level of onboard automation, such that the user feels in control and also has low cognitive load? That this must be really tricky. In prosthetics, it's a mess, literally. What do you answer here? It's about the shared autonomy, right? Where do you draw the line, or how do you balance it?
The answer is in the question. That the control in a way that the cognitive load is low?
I think the question is more so you want to give the user enough control so that control is transparent. The device does what I want the device to do. But then at some point, the device will do something automatically, let alone just the low-level control system for the motors. Where do you draw the line? Can the line be adjusted live, for instance? This would be my additional question.
This is quite, but everything that has been, let's say, commercialized and then a certain level of autonomy, then will take the responsibility of any accident that will happen.
Right.
So, I mean,
good point.
So the more the control is under the wearer or the person that is using the machine, the more will be safer. So if we consider, for example, the application that I propose with the camera, if the camera fails,
yeah, right,
it doesn't mean that instead of climbing the stairs, you attempt to go down the stairs and you will fall. Basically, it does not assist in lifting the leg more, and you will have to climb the stair by your own. This means that still the system is controlled by the person himself or herself. So the autonomy should be completely shared, in my opinion, by the wearer. And this is something that happens, for example, in I don't want to say autonomous driving, because autonomous driving is fully autonomous, and we know that sometimes there are, let's say, mistakes and failures that sometimes are also quite heavy. For wearable devices or devices with higher level of risk, let's take, for example, a motorbike. Even if you have electronic intervention, if something happens, the fault most of the time is of the pilot. It's not of the system.
Right. I believe you have a problem. So the smaller level of residual activity is in the user, because then you have to have a more and more autonomous machine. So
there should be a residual activity from the user, otherwise this machine cannot be used.
Yeah, of course, because we can't really know what the user wants to do. Still, if the user has bad signals or jumbled or some form of slight cognitive impairment, like the person we saw in Connor's experiment. So this person who could hardly walk, and then you start giving him the right cues, and bang, the walk looks almost normal, right?
Yeah, but cleverly, Connor can depress much more because his own research, he was giving cue. He was not giving a portion of the assistance that was too intrusive. Connor, and go ahead, of course, it's your research.
Yeah, like I think it was like it was a low level of assistance, like it was like relatively low percentage of normal hip flexion torque, but it was probably enough to be doing some mechanical assistance, but it was also enough to be kind of giving a cue for the person, and it could have been some combination of those. So I don't think we really know is the honest answer. But I think kind of, Claudio, your point's like really interesting as well. Like I think a lot of times we're thinking about like what is the perfect controller for a perfect device and scenario. But having like the idea of being able to kind of like have the user adjust what's going on in terms of like, is it shared kind of control, or is it kind of control or like assistance level, or is it some other parameter? Or also thinking that changing over time, having a clinician remotely see how a person is doing and adjusting what a device is doing. I think, you know, we have the capacity with like Internet of Things now to have these devices have live software upgrades like over time, or controller upgrades. So I don't think it always has to be only one way. I think it can kind of like, and probably should change over time. Yeah.
I have two last questions so that we exactly get to 3:05, and we will all have to move to our next meeting possibly. So Marek Shirotovich from my own group, by the way, asks, so you think that integrating sensors to monitor interaction forces is always worthwhile? More generally, what are the salient trade-offs going into sensor selection? In a nutshell, what kind of signals do you think are really important to gather from the exosuit, from your device?
Robust, repeatable over time.
Well, right. This would be also my question. So.
Yeah.
Yeah, right. But this links to the previous issue, right? As people learn how to use your device, they start producing better and better signals. This is clear in prosthetics, right? They start feeling that if they do some specific thing, then the device goes well, and so they start, insisting on that point. It's like they twist around their input space, and in the end they produce better clusters. Let's say this in terms of machine learning, right?
To answer also the question, I would also say, again, it depends a lot on the goals of the use of the device. If you care about the amount of participation, muscular participation of the patients, maybe it's wise to measure some force interaction or EMG activity. It's wise to do this in a therapeutic approach. If you don't care because you just want to support the patient to get from A to B, then maybe you don't need to measure it because you don't care. And maybe sometimes you care about the instability of the shoulder. You might measure the folding out of the scapula. You can also measure this, for example, etc.
Yeah, I think also one of the things to think about is what sensors do you need for the purpose of developing and optimizing your control algorithms, and what sensors do you actually need for the system to function independently, either in the clinic or in the community. And those are often very different, because we want more information as we're developing and figuring out what we need versus what we actually ultimately need to pare it down to make it as simple as possible.
Totally agree on that. Good. Last question is from our colleague, Mohamed Buri. Mohamed asks, would you say that there are more needs of soft exosuits for upper limbs or lower limbs? Is there more need of exosuit in which realm of rehabilitation? This is, I have no clue here.
So one could count just the number of cases, the prevalences. Maybe there are more people suffering with lower extremity impairments. I don't know. Depends on the subgroup you want to check. That could be one important number to see is there a market, for example, worth to develop something. It depends a bit also what you define as a need.
Yeah, that's correct. That's correct.
Would you say that the controls for lower extremity exosuits are, I don't want to say simpler, but the motions of the lower extremity are a little more predictable than I would say the motions of the upper extremity? And do you think that has, a major role in terms of what's been developed so far?
Yeah, for a clear opinion, most lower extremity activities are periodic. and less versatile. And that makes the development and control much simpler. Upper extremity, you need to provide power because it's also not periodic. You cannot do it ballistically. And you have so many fingers and functions with the hands. That's basically, from my point of view, the bigger challenge for the upper extremity.
Mm-hmm.
Anatomically speaking, also is much more complex. I mean, we talk about the shoulder, and of course, I mean, we know, but that's why, and also, you know, the predictability of the signals that you have to collect to drive the control of the system for wearable robotics. It's something that can be extracted also using initial measurement units, devices that are on the shelf. Yeah.
And, you know, in prosthetics, we see a prevalence of all kinds of machine learning applied to typically EMG, mostly in upper limb prosthetics. Lower limb, there's a lot of help that comes also from sensors mounted in the prosthesis, because, you know, a leg is bulkier, heavier than an arm. So, yeah, that's good.
So the final response to the question of Mohammed Puri was like basically 50-50. There's more in lower limb because lower limb, it's easy to understand. I mean, you have to scale up basically the assistance, but the predictability, you want to restore walking. That's the thing. While
that's right.
Functionality in the upper limb is a multi-manifold system.
That's right. Good. My friends, 5 minutes past 3, I say we close the meeting here. It was an exciting and really informative time, and even quite fun, I have to say. So big thank you to Lorenzo Masia, Robert Riener, Conor Walsh, and my co-moderator, Kathleen O'Donnell. Sorry. And so I hope I will see you again at some point during this year for the upcoming webinars. And so far, thank you all for watching and joining, and goodbye.
Thank you.
Bye.
Thanks, everyone.
Ciao, ciao Robert, ciao Conor, ciao Claudio, Kathleen. Thanks a lot.
Bye-bye.
Ciao.